This is lecture 4C on critical points. This lecture is actually on more than critical points. It describes how the function behaves either on an interval or at certain points, and how that relates to the first and second derivatives, if they happen to exist. So the first set of properties has to do with how the function behaves on an interval. And these include words like increasing or decreasing, and concave up and concave down. The second set of properties has to do with how the function, about certain critical points along that function. And these could be functions where it's a maximum, or it's a minimum, either globally or locally, or where there's an inflection point. For all these properties, you could write some kind of long definition for it, but the idea is if you have the derivative, looking at the signs of these derivatives will often help you identify these properties. Okay, is a function increasing or decreasing on an interval? You could try to look at each single point and say, yeah, it's getting bigger, it's getting bigger, it's getting bigger, check out 2 more points. Or is it decreasing? You could start looking at the values and say, yeah, it seems to be getting, smaller and smaller and smaller as I go up in x. You could do that. But if you happen to have first derivatives, you take the first derivative, and if the first derivative is positive on that interval, the function is increasing. If the first derivative is negative on the interval, the function is decreasing. These properties pertain to the function whether or not it has a derivative. Say the function is not continuous. Say the function doesn't have a derivative somewhere in the interval, but instead has a jump. It could still be increasing or decreasing, but you could not use the first derivative test. Now I want to present some vocabulary, and that has to do with adjectives. I guess that would be adverbs on the increasing or decreasing part. Okay, strictly and monotonically. Monotonically to me always sounded stronger than strictly, or I don't know, it sounded about the same. Here's the difference. If the function is always increasing, then we would use inequalities like we did above with greater than or less than. That is a strictly increasing function. All right. If instead the function increases but then levels off into a little plateau, and then increases again and maybe levels off into a little plateau, that function is monotonically increasing. Or vice versa, monotonically decreasing. Be decreasing and then kind of level off, and then decrease some more. Right. In that case, the inequalities would be less than or equal to or greater than or equal to. These definitions are correct. Sometimes people use them in another way. Sometimes they will say monotonically increasing when they mean strictly. But that can happen. So when you look at the terms and you see someone using them, look a little bit further and find out exactly how they're using them, because sometimes they're not always used this way. Now the second property that we're going to look at for functions with regard to intervals is concavity. If it's concave upward, then that section of the graph would hold soup. If it's concave downward, then soup will spill out of it. Those are precise definitions for you. Right. You can look at this in terms of the function and the first derivative, such as that the function always lies below its first derivative and all that kind of thing. But how are you going to apply that? You're not going to apply it. You're pretty much going to eyeball the graph. If the function has 2 derivatives, though, the sign of the second derivative will tell you whether it's concave upward or concave downward. You have to have 2 derivatives, and if that second derivative is positive on that interval, it's concave upward. It will hold soup. If the second derivative is negative, it's concave downward, and soup will spill. Therefore, it's negative because you don't have soup. You've lost your soup. All right? So I'll show you a picture to make that clearer. All right. Here in this picture, we could say that right in this interval here, the function is increasing. In fact, it is strictly increasing. And this does have a first derivative, so the first derivative is positive. It's positive where the function is increasing. Right through here, the function is increasing. The first derivative is positive. Right, through here, the function's increasing and the first derivative is positive. In this region, the function's decreasing and the first derivative is negative. Same for both of these sections over here. The function was decreasing, the first derivative is negative in both of these small sections. However, it's 0 right there. That means it is monotonically decreasing as opposed to strictly decreasing. It's strictly decreasing on the two subintervals here, C4 to C5 and C5 to B, but overall from C4 to B it is monotonically decreasing. Don't worry too much about those words. That's more for the future, for future math classes than it is for right now. So increasing and decreasing. If it's increasing, the first derivative is positive. If it's decreasing, the first derivative is negative. The second property for intervals was concave up and concave down. Right here, through here, the graph is concave down. It's concave down because soup would spill out of it. Obviously here, it's concave up. Okay. Even on some smaller sections, like right through here, it's concave up. Here it's concave up again. Looks like it gets concave downward for a little bit through here. So you can see it changing. So if I look right through here, it's concave up. Somewhere in here it changes and starts being concave down. So you don't have to have it totally turning over like a soup bowl. All you have to do is look at little sections of it. Right through here, it's concave down. Now in this case, the second derivative would be negative because it's concave down. Right through here, the second derivative would be positive. So I'm going to say all this once more. On the interval where the function is increasing, if it has a derivative, the derivative will be positive. On the intervals where the function is decreasing, if it has a derivative, the first derivative will be negative. When it comes to being concave, you look at the second derivative. Right? If the second derivative is positive, it's concave upward. If the second derivative is negative in that area, it's concave downward. Now we'll talk about endpoints and critical points. Now we're talking about the function as it behaves at certain points, not on certain intervals. So there's two important categories for points: the endpoints and the critical points. A critical point is an interior point in the domain of f. It's interior to the domain of f, where the first derivative is either 0 or the first derivative is not defined. At these critical points, the function can have an extreme point, meaning maximum or minimum, or it can have what's called a point of inflection. And at the endpoints, the function can also have these maximum or minimum, and now we have to have some more vocabulary. All right. There are two kinds of maximum and minimum values, or I should say maxima and minima values. Okay. Global and local. Some people also use the word absolute. Okay, but we're going to use global and local because they contrast with each other, so I like that. Okay. For a point to be a local minimum, it can occur anywhere in the domain except at the endpoints, because a local minimum has to have an open interval about it. And at the endpoint it wouldn't, because part of the interval would be closed at the endpoint. Okay? So local is in the interior of the domain. The global can be anywhere, at the endpoints or in the interior. All right, so I'll say that again. A local maximum or minimum can occur anywhere in the domain except at the endpoints. The global maximum can occur anywhere in the domain, including at the endpoints. The other point is that the function must actually attain these values. It can't just approach them, or they can't just be there as in the limit. The function actually has to have that value in order for that to be a global or local maximum or minimum. So say you have a function that's strictly increasing on some interval, it will not have a global max or a local max there because it never it's always getting bigger and bigger and bigger. It never hits any particular point. Now the local maximum and minimum, you could have a whole bunch of those. But when you have a global max, you say 2 is the global maximum, there cannot be another global maximum such as 5. Then 5 would be the global maximum. So there's only one of them. It can occur many points, many places in the function, but only one value for a global maximum. For the local max and min, you can have many values. Also, a max and min can be both global and local, and a function might have none of them. So here we are back to this picture again, and I'll point out, I think that there's an error here, but the function comes up here and it hits a local maximum. It also hits another little peak here, right? It has, this is a local maximum, this is a local maximum, however, it's also the global maximum because it's the most maximum of the maximums. Here is a local minimum. All right. They use the word absolute here. This is a minimum on this. This is a global minimum. It's also a minimum because it's occurring at the endpoint. I'm going to say this is closed, although I don't think they meant that. But if this was closed, this would be your global minimum, but it would not be a local one because local needs to have this little, see how I've drawn it? Little neighborhood around it. Here's a local max, has a neighborhood around it. So does this. This has a neighborhood around it, so it can be a local max. But the most maximum of the maximums, or then you can compare at the endpoints, that would be your global max. So for a global maximum, this global maximum would occur when x equals c if the value of the function there is greater than or equal to the function at all the other points. Notice it could be greater than or equal to. So if you had a straight line, okay, how about a global minimum? That means the value of the function is less than or equal to all of the other values of the function in the domain of f. Remember, global maximum can occur at the endpoints. For the local maximum means that the function is greater than f of x for all x in a little neighborhood about c. Neighborhood meaning an open interval. Same with the local minimum. The value of the function is less there when compared to all of the other function values in an open interval about c. And there's no specification on how big that interval has to be. It could be very, very small. But the where it cannot occur is it cannot occur at the endpoints. There's another critical point. It's called a point of inflection. This is a point in the interior of the domain, and two conditions have to happen. First, although I've listed it second, the first derivative has to exist. And second, it has to change from either concave up to concave down or vice versa. So you have the first derivative has to exist there, and then the concavity of the graph changes from up to down or down to up. That's called an inflection point. I'll show you one of those now. Okay, look right here. First derivative is 0, so it's a critical point, and it's concave down on this side. It's concave up on this side. Right here, the f prime, the first derivative is 0. That is a point of inflection. Here's another one right over here. So now you know what points of inflection are. Max, min, point of inflection, sort out the local and global. And remember that if you have these derivatives, you can use them as tests. All right. So now you want to use these derivatives to test for these critical points and these maximum and minimums. Remember, a critical point is a point where the first derivative either doesn't exist or is 0. So Fermat's theorem is written in a kind of a, well, here it is. If the function has a local max or min at x equals c, and if the function has a derivative at c, then the first derivative is 0 there. Notice it has two ifs. Okay, so if it has a derivative and it has a local max and min, then the derivative is 0 there. But we just saw how the derivative could be 0 at another point that wasn't a max or wasn't a min. Okay, that's what the next words mean here. The converse does not hold. Just because it has a zero, just because the first derivative is zero there, it does not necessarily mean there's a local maximum or minimum at C. It just means there's a critical point and you have to check further. All right. And it doesn't mean that the maximum and minimum are only where the first derivative is zero. Because there's points where the first derivative is not even defined, and yet that is a local min, perhaps even a global min. So the note I put here is note that there are two ifs in Fermat's theorem that makes it sort of a little bit restrictive. And I put it in the category of it works when it works. So here's an example. Here's the absolute value function. All right. Right at this point, it does not have a first derivative. F prime doesn't exist. Remember that F prime is -1 if it's less than 0, +1 if it's greater than 0, and not defined at x equals 0 for the absolute value function. All right. It doesn't exist there. It is a critical point. F prime does not exist. But if you look at this, it is a local minimum. In fact, it is the global minimum for the absolute value function. It is the lowest of all low points. In fact, it is the low point. Okay, so it's a minimum, a global and a local minimum at the same time. But the first derivative is not 0 here. So this is just pointing out to you that just because you find the first derivative to be 0, don't run off and say, I've got a max and a min. You have to check further. All you've done is find a critical point. You must also look at points where the first derivative does not exist. Here's another example. This is a cusp, correct? So the first derivative does not exist here, but this is also a maximum, and it's a global and local max. On the other hand, here's a local max and f prime is 0. Here's a local min and f prime is 0. Okay, let's say that the first derivative is equal to 0. Then you can look at its behavior, the first derivative, as you go through the point x equals c and figure some things out. If this is a maximum, if f prime, the first derivative is increasing on the left and then decreasing to the right of it. In other words, it's going up towards the max and down away from the max. Okay. Or you could look at it the other way. If f prime decreases, then you hit the critical point, and then f prime increases away from that, then it's a minimum. Now, if you happen to have two derivatives, then you can use both the first derivative and the second derivative to see if that critical point is a local max or a local min. Right? So f prime, first derivative is 0. I know it's a critical point. Look at the second derivative. If the second derivative is less than 0, then that means it's concave down. So that point is a local max because it's on the top of the soup bowl, when the soup bowl is opening downward. Okay. On the other hand, if the first derivative is 0, you look at the second derivative and it's greater than 0, then that critical point is a local minimum. And note that the point could a point could be still max and min without satisfying these conditions. All right. If you didn't have a second derivative, if you didn't have a first derivative, you can still have a max and a min. It's just that if you have these, then you can use them. I'm going to state here without proof some theorems that are sometimes useful. Rolle's theorem. If f is continuous on a closed interval ab and differentiable there, and if fa, the function is the same at both endpoints. So it's closed on intervals, say, 2 to 4. And the value at 2 is 10, and the value at 4 is 10. Then there is at least one point in C such that f prime is 0. All right, and f is continuous. Remember, f is continuous here. Okay, what does this really mean? What does this mean if you speak casually? It means that the function starts and returns to the same value, starts on a value and returns to the value somewhere along the line. It had to peak out or bottom out at least once. That's what it's saying. And here's the mean value theorem. if f is continuous on a closed interval AB and it's differentiable there on the open interval AB, there exists some c in AB such that the derivative there is equal to the crude derivative, shall we say, of taking the function at the endpoints divided by b minus a. So what this means casually, if you think about velocities and displacements, is that if you go along a path with different velocities, there was some place along that path where the instantaneous velocity was equal to the average velocity. That's what the mean value theorem says. And then from that comes this very important corollary. If you have two functions and they have the same derivatives everywhere, then the only difference between them is some constant c. Then the functions are equal plus or minus a constant. And this generates, for example, look at these curves. These are all parabolas. You can just look at all those and see that the curvature is the same. The first derivative is the same. But the only difference between them is that they are displaced. So if you have two functions with the same first derivative on some open interval AB, the only difference between those functions is a constant, a vertical displacement. So now I'm going to try to give you a procedure for checking for these maximum, the minimum critical points, and the concavity. I hope that in some way I've condensed the material in the book so that you can use it as a checklist. Remembering that you've got definitions for how the function behaves, increasing, decreasing, concave up, concave down. You've got a vocabulary for certain points, point of inflection, maximum and minimum point, local max, local min, global max, global min. Those all have very specific definitions. If you happen to have derivatives, you can use these derivatives to test for those special points or to test for that behavior on the interval. However, it doesn't work the other way. Sometimes you don't have derivatives available. You can still use those definitions. It just takes a lot of words to state that. All right, so what's called a closed interval method. You're looking for global max and min, and it's a continuous function. Find those critical points. That means find all the c's where the first derivative is 0. Then look at the function at the endpoint. The largest of these is the global max. The smallest of these is the global minimum. Well, I violated my own principle here because I usually write global, but I wrote absolute. So here it is again. You've got the functions continuous on an interval, AB. Then look at all the derivatives along there. Find any point where f prime equals 0. Right. Evaluate f at the endpoints. The largest of these values is, actually that should say f prime is 0 or f prime doesn't exist. Sorry. Then evaluate the function at the endpoints and at these critical values. The largest of these is a global max. The smallest of these is a global min. And here is sort of the general procedure that is suggested for just basically eyeballing functions. So when you look at the functions, try to find all the important intervals and points along the function. If there are any obvious discontinuities, jumps, or cusps, look carefully at, especially when you have a piecewise function, look at if there are any jumps right when you switch from one piece to the other piece. Okay. Then you can look for vertical asymptotes. For rational functions, these are the values of x where the denominator will go to 0. Okay, be careful with trig and inverse trig functions as well. They have vertical asymptotes. And then check out for horizontal asymptotes. That means look at the behavior of the function as x goes to plus or minus infinity, assuming the function is defined on the real line and not on some closed interval. The next important point that I didn't mention yet, and that's symmetry. Is it even, odd, periodic, or is there no symmetry? If it's an even function, you know it's reflected about the y-axis. It's a mirror image on either side of the y-axis. And the way to test for it algebraically is to take your function f of x, substitute negative x into the equation. If that doesn't make any difference and you still get back the original equation, the function's even. For odd functions, you do the same test. Replace x by minus x. If after you work out the algebra you get the negative of the original function that you started with, then it's an odd function. It's said to be symmetric about the origin. And always, if its domain's closed, check out the values at the endpoints. And now you take the first derivative. what are the critical points? At the critical points, the first derivative either does not exist or is 0. Okay. Determine the sign of the first derivatives between the endpoints and the critical points to find out if the function is increasing or decreasing. Where the first derivative is positive, it's increasing. Where the first derivative is negative, it's decreasing. And at this point, you might be able to find global and local maxima and minima, if any. Continuing along, let's take the second derivative. The second derivative will tell you where the function is concave up or concave down. If the second derivative is positive, it's concave up. If the second derivative is negative, it's concave down. You can use this to identify your maxima and minima too. Are there any points of inflection? At an inflection point, the second derivative changes sign, like from plus to minus or minus to plus, and the first derivative exists. Basically, that's about it on these definitions. They are a little hard to sort out. I'm going to reiterate what I said. There's properties that identify what the function is doing on an interval. There's properties that have to do with how the function is behaving at certain points. On the intervals, what you look for is increasing or decreasing, concave up or concave down. If you happen to have derivatives, then it's increasing where the first derivative is positive. It's decreasing where the first derivative is negative. It's concave up where the first derivative is positive. It's concave down where the first derivative is negative. That's about it for intervals. Then the points are called critical points, and it could be a maximum point, a minimum point, a point of inflection, or perhaps neither. If you have derivatives, you look to see what the first derivative is doing. If the first derivative is 0 or non-existent, that is some kind of critical point, although initially you don't know what kind of critical point it is. It could be a maximum, could be a minimum, could be an inflection point, something else. Okay. If you have that second derivative and first derivative, if the first derivative is 0 and the second derivative is less than 0, you have a local maximum. That would be this case right here. If the first derivative is 0 and the second derivative is positive, you have a local minimum. If the second derivative is changing sign, so it's 0 right here from positive to negative, and the first derivative exists, that's called a point of inflection. Now, some points where the derivative does not exist doesn't mean they're excluded from these definitions. This, for example, is a global and local maximum, but f prime doesn't exist there. And you can't use f double prime to tell you what it is either.